Symmetric encryption refers to the goal and corresponding primitive that tries to provide privacy of encrypted data based on a key that's shared between the sender and receiver and private to them. It's arguably the most basic canonical goal of cryptography, one with which in many minds cryptography is identified. Now at this point one may ask, haven't we been encrypting all along? What about all those block ciphers and PRFs and so forth? Those are tools. They aren't end goals. They don't directly solve the problems of interest. We would not even at this point have given a definition of what privacy symmetric encryption needs to satisfy. Remember that modern cryptography builds its primitives in a kind of Lego way, and we started from the bottom. We have talked about the tools like block ciphers and PRFs, and now is the time to put them together to get the first primitive of actual applied interest. Of course, we will exploit these tools, but symmetric encryption isn't equal to a block cipher. It's in fact quite interesting how we make the transition from one to the other. Whenever we have a cryptographic primitive, its first element definitionally is what we call syntax. Syntax simply says what you need to describe in order to give a specification of a scheme. And in this case, a symmetric encryption scheme is a triple of algorithms. So to specify it, I have to give you descriptions, either mathematically or in code, of 3 algorithms called key generation, encryption, and decryption. The key generation's algorithm's job is simply to spit out a key of some size. Typically, this is just a random string of some length, for example, a 128-bit AES key. The encryption algorithm run by the sender will take this key and, under its influence, take also a message and return an output called the ciphertext. The decryption algorithm takes the ciphertext and the same key is used for encryption and produces a message or perhaps a special symbol bot indicating failure to decrypt. The key generation algorithm is run once. Once the key is generated, it is magically communicated to sender and receiver, and we don't use it again. In this abstraction, the sender and receiver don't exist, nor does the process of communicating the key. We simply talk about the algorithms that the entities will be using. The adversary is going to be sitting somewhere on the line and will be obtaining the ciphertext. What is that little $sign for? This indicates that this algorithm may potentially be randomized. So it may internally flip coins and thereby have different outputs even if you feed it twice the same inputs. And we will see how that comes up and why it's necessary. The key generation algorithm also is similarly randomized, and that's necessary for security. But the decryption algorithm is going to be required to be deterministic. So every time you state and provide a symmetric encryption scheme, your job is to say how these 3 algorithms work. Before security, we have the requirement we call correct decryption. That simply means that decryption does truly reverse encryption. Otherwise, we are not communicating information faithfully. So the requirement says that if I take any specific key and fix it, and now if I start encrypting a message M under it to get a ciphertext C, when I decrypt C under that same key that was used for encryption, I will indeed recover the message. This is true even if encryption is randomized. Here it is more formally, for every possible choice of key that may be output by the key generation algorithm, meaning has some positive probability of being output, and for all M, all messages M, what happens if I encrypt under the key the message to get a ciphertext and then decrypt? I should get back M. This says that happens always by saying it happens with probability 1. Why a probability? Because encryption may be randomized, so there's something over which to take a probability. Now, here we see mention of something called a message space. It's often the case that different encryption schemes will encrypt only messages of certain formats or lengths, and accordingly, the correctness condition of decryption applies only to messages from that space. And usually when we give the scheme, we should also be saying what this space is. So we have block ciphers, and if you're going to start designing encryption schemes, it's quite natural to be using them. And a mode of operation is a symmetric encryption scheme based on an underlying family of functions, which in particular might be a block cipher, but doesn't have to be. That depends on the mode. So here we'll take a family of functions with key length k, input length n, output length l, perhaps a PRF. And we are going to be wanting to use this to encrypt messages that have a length that may be too large to be put into one block of either input or output of the family of functions. So we will be breaking messages into blocks, and I'll usually use xi to denote the ith block of a string. We might also break ciphertext into blocks with similar types of notation. The length of a block will vary. Sometimes it's n, sometimes l, sometimes it could be even something else. Whenever we use a family of functions, or usually at least, the key generation algorithm simply picks a random key for this function family and returns it. So the key for encryption is just a key for the family of functions. And with that, we can usually omit mention of the key generation algorithm. Now, if you have a block cipher, it seems at first our encryption problem is solved. What you can do is you run your message through the block cipher using as key the key that your symmetric encryption key generation algorithm has provided you, which is the key for the block cipher, which the encryptor and decryptor know. And the ciphertext is the result of the block cipher. And we've discussed various different security properties that this may have. So are we done? Well, this has a limitation, which is that you can only encrypt one block messages, and that's not what we want to do in practice. We want to encrypt messages consisting of many blocks. So at least the first task we face is extending this block cipher encryption to many blocks. But that's actually quite easy to do. Here's the natural solution. Break your message into blocks. Say you get little m blocks, and just run each of them separately through your block cipher, all with the same key that you fixed and is shared between sender and receiver. You get m blocks of ciphertext, and that sequence is your encryption ciphertext, which is the thing that's transmitted. Here you can see it in code. Remember that the symmetric encryption scheme is this triple of algorithms. We already said how k works. It just returns a random key for the block cipher. And here are E and D. They break the message into blocks and run the block cipher E separately on each block to get the ciphertext described block by block, and then communicate the entire ciphertext here. We see that the fact that the block cipher is a block cipher, meaning once you fix k, it induces a permutation that has an inverse, is important to decrypt. When you decrypt, to recover the message from the ciphertext block, you run the inverse block cipher algorithm. Okay, so we have an encryption scheme. Well, what's wrong with that? It turns out that this is not very good from the security perspective, and this is where we start developing some more understanding of what security is, and things get kind of interesting. One property that this encryption scheme, which we'll call electronic codebook mode, has is that if you twice encrypt the same message, you get the same ciphertext. Well, of course, since it's deterministic once you fix the key. So if M1 equals M2, each of them is some sequence number of blocks, then C1 will equal C2. At at first, this seems natural when you think about codes as we understand them in popular cryptography. They are indeed mappings of messages to ciphertext, where once you fix the key, there's a unique ciphertext associated to each message. But we will argue that this is actually not desirable from a security perspective. So here's an example to demonstrate that. Suppose that we know as an adversary that there are only two possible messages being encrypted. Let's represent them by the string of all ones and the string of all zeros of length, the block length of the block cipher. Think of them as yes or no. Why might this happen? Well, maybe our application has that form. Maybe there's a command to do or not do something, buy or sell something, or simply a vote, yes or no on some proposition. Everybody, including the adversary, knows that the messages have this format. But whether it's yes or no is something we want to hide. It's crucially important. And our claim will be that electronic codebook mode fails to hide this. And so let's see why. Here, the message is one block long. So when you run electronic codebook mode, you're just running the block cipher on that one block. So encryption, which is the script E, and the block cipher, which is the normal font E, just become equal to each other. Now, let's say that we are considering an application involving voting, and there's some polling station, let's say, where people go and they cast votes. And two people enter. The first one has a vote M1, the second is a vote M2. Both, of course, are either yes or no. And they cast them, and the polling station then encrypts them and transmits them to a tally center. The polling station and tally center share the key under which the encryption is performed, and ECB encryption is used. So what does the adversary who's eavesdropping see? It sees two corresponding ciphertexts C1 and C2. The first encrypting M1, the second encrypting M2. Okay, and it's trying to figure out what these votes are. Well, already one thing pops out. It will determine whether the two votes are equal or not. So if it turns out that both these people voted the same way, the adversary learns that even though it doesn't know what they voted. But that's already a loss of information that we'd prefer to not have happen. But here's another scenario, and this illustrates how it's important and interesting to think about different scenarios. Let's say the adversary was one of the voters. Why not? So the adversary is the one who cast the vote M1. And of course, then it knows it. Say it's a yes vote. It wants to figure out what its neighbor M2 has voted, meaning what M2 is. And it can figure that out completely. Why is that? It simply checks whether this ciphertext equals this one. If they're equal, M2 must be a yes vote, and otherwise it has to be a no vote, because C1 and C2 are equal if and only if M1 and M2 are equal. So given C1 and C2, you can determine whether or not M1 equals M2. And now knowing M1, that tells you what M2 is. So this example shows us how, depending on applications, we need to assess security in a possibly novel or creative way to see whether some scheme is giving us what we want. The weakness of ECB in this regard is quite well known and popular, and one of its common images out there is this encrypted penguin. And as you can see here, they took an image of a penguin and performed electronic codebook encryption. But given that the pixels in the penguin image have a lot of commonality, you see that the encryption has failed to hide the picture. So all the pixels of one type have stayed of that type. And although the colors have changed, you can recognize the penguin quite well. So ECB is not kind of what we're looking for. Okay, but then one might think one has hit an insurmountable stumbling block, because why isn't it the case that this attack actually works for all encryption schemes? So take an arbitrary encryption scheme, and again, suppose I want to use it in a setting where the only possible messages are yes and no. And the sender is transmitting two ciphertexts, one encrypting M1, the second encrypting M2, under a key K that's unknown to the adversary. But the adversary knows that the first message is a yes. It's trying to determine whether the second is yes or no. Well, let's do the same attack as we did for ECB. We check whether C2 equals C1. If they're equal, M2 must be a yes, otherwise it must be a no. Is that correct? Well, it is if encryption was deterministic. When you fix a key and input message, if the encryption algorithm always returns the same ciphertext, then this attack actually works. No matter how you design the encryption scheme, its determinism alone gives rise to this attack. And this is why it may seem a little counterintuitive if your understanding of encryption is purely that coming from sort of a popular view in which it's a code mapping messages to ciphertext. What it tells us thus is that if we want encryption to be secure in the kind of usage we are considering, the encryption algorithm needs to be randomized, meaning it's going to flip coins, and even if the same message is encrypted twice, due to these internal coin flips, you're likely to get back different answers. So now we write it like this with a $sign, and even with K and the message fixed, there's some distribution over the output ciphertext. Even if M1 equals M2, while there will be some probability the ciphertexts are equal, it may be quite small. And at that point, we can hope for much better security. So, when we start conceiving of this idea of randomized encryption, we have to think, well, but how are we going to design schemes to do that? And one difficulty that appears to arise is that if encryption under a particular key and message can create a whole slew of ciphertexts, then how will decryption know that they all decrypt to the same message? Somehow decryption has to have that capability that it can decrypt all of these back to the original message. But we'll see how to do things like that soon. But first, it may be worth commenting on the kind of historical and philosophical implications of what we've just said, because this is quite a departure from classical and conventional notions of what is encryption, which is that it was a code, like a substitution cipher, so that once you fixed a key and message, there's only one possible ciphertext. But this is saying that no such code is actually secure, and we need to look to encryption mechanisms which associate to each message a number of different possible ciphertexts. Now, this is well understood at this point. Here, for example, is a Stack Exchange question by someone who wants to know, why shouldn't I use electronic codebook encryption? And why is the person asking that? Because by now, even libraries like Java will warn you. If you try to use ECB, they'll tell you it shouldn't be used. And so the person is asking for an explanation. And if you took this class, you could easily give them an explanation. And someone took the trouble of writing quite a nice long one and included our little penguin example. What you see here is the original image. Look what happens when it's ECB encrypted. You can still recognize the penguin. And look what happens when you use a good mode of operation like we'll study. And now you see that the image is completely obscured. And the person also points to many other reasons and goes on to tell you how to fix things and things like that. So here's our first example of how you might encrypt with randomization. And it's the very well-known Cipher block chaining mode. Mode again means simply a symmetric encryption scheme based on an underlying block cipher. So we are assuming again that this E here is a given block cipher. And this is the symmetric encryption algorithm. How does it work? It breaks the message into blocks. The length of each block is the block length of the block cipher. It will be running each message through the block cipher with our fixed key k just as before. The difference is that something is added to the message before that happens. Some C0 is added in here, and then whatever ciphertext is obtained here is cascaded back in over here, and you encrypt only after that. What is this C0? It's called the initial vector, and it's actually something chosen at random by the encryption algorithm. And this is where we see the randomization step happen. And once that's done, this code simply encapsulates how this picture works. Now notice that what's returned, the full C, includes C0. So the ciphertext is one block longer than the plain text and includes the initial vector. Perhaps at this time, there may be a bit of a question of the form, okay, we use randomization, but we've provided the randomness to the adversary by putting it here. Is that okay? It turns out that's okay. We'll get to that later. Now, why in fact do we provide it? Because otherwise you wouldn't be able to decrypt. So let's look at decryption. What decryption does is it says, I know how to reverse this operation because E is a block cipher and I know the key, so I can go backwards. So from C1, I can arrive at this point. If I know C0, I can add it back in and get the message block here. Similarly, from C2, you go backwards, come here, you know this, add it in, get M2, and so forth. And that's decryption. So correct decryption relies on E being a block cipher and relies on the initial vector being available. Okay, and this is a popular encryption scheme. Here's another one called counter mode, another mode of operation for a block cipher, which is by now possibly even more popular than CBC. So again, we are going to encrypt the message as a sequence, break up the message into blocks. So now counter mode is a little more general than CBC in that you don't need a block cipher. You can use a family of functions that's not a block cipher. So we're going to do it that way here. K is still the key length, but the input length and output length could even be different. So there could be n bits of input and L bits of output. And it's a family of functions. And there may not be any way to reverse it. So it's not a family of permutations. Okay, a little bit of notation. If I have an n-bit string, x plus I denotes kind of what you would expect. You think of x as an integer and add I, and then think of it as string again. And to make this make sense within the boundaries we have, you will do the addition modulo 2 to the power n. All right, so now let's come to look at how encryption is used. We have our family of functions, and the encryptor and decryptor have their key k. The message is broken into a sequence of blocks, and the blocks are of length this L over here. So the length of each block is the length of the output of the family of functions. Now previously, we always started by enciphering under the block cipher the message or something related to it. That's not what happens here. What happens is that the encryption algorithm starts by picking at random an n-bit string of this length n here. And then it creates the sequence C0 plus 1 plus 2 up to plus m, where m is the number of message blocks. So a very structured sequence of strings, just consecutive but with a random starting point. And to each of these, it applies the function family with the hidden key and gets an output. These outputs P1 through Pm are viewed as one big pad, and then the message is simply XORed to that pad, and we can think of it as happening block by block. Each P sub I has length L since it's the output of the family of functions, and hence you can add the corresponding M1 into it, and that gives you these ciphertext blocks. C0 is also part of the ciphertext, this original one over here, so the grayed out thing is the full ciphertext that's transmitted. Okay, and now let's look at decryption. What's interesting here is that we're going to be able to decrypt despite the fact that E itself has no inverse. How does it work? Well, given these ciphertexts, the adversary first looks at this and reconstructs this sequence over here. It just has to add 1 and 2 up to M, where M is the number of blocks in the ciphertext over here. It has E and K, so it can, just like the sender, run through and compute the P's over here, the pads. And then by adding to the ciphertext to those, it recovers message blocks. So the message is recorded by this formula. And that's it. A few little things that may be worth remarking. This ciphertext has M+1 blocks, not all of the same length. This is N bits. These are all, each of these is L bits. Okay. Now, there are some interesting elements about this scheme. One of them is decryption, as we already said, does not use any inverse. Now, you could, and we normally would, use a block cipher for E in this scheme so that N equals L. But nonetheless, there will be no inverse used in the decryption process. Decryption will still use only the forward direction. But sometimes it's nice to have a mode which works with a family of functions that's not a block cipher, and that there's no inverse. Another implementation benefit is that encryption and decryption are parallelizable. In CBC, the chaining precluded that. But here, if you want to encrypt a multi-block message, you can operate on the different blocks independently. You can even pre-process the creation of these pads and just have them waiting around until the message arrives. So there are many different efficiency advantages over here. So again, we can go and see how all of this kind of stuff plays out. Here are some questions about how the security compares. It says, should I use ECB or CBC mode for my block cipher? Which mode is better, and how do I decide which one to use? Are there any other modes which are better? Well, we'll be answering questions like that. So this is an encryption scheme called GCM, Galois counter mode, that's used in TLS, in the TLS protocol. And if you look at its description, you see that internally it's using counter mode, and that's visible over here. So there's a key K, and it's taking counter values, counter 1, counter 2, starting from counter 0. Increment means add 1. So this is like our C0, C0 plus 1, C0 plus 2. Apply here it is a block cipher to get these pads over here, add in the plain text, which we call the message, and get these ciphertext blocks. Now, a lot of other stuff is happening. That's in order to add authentication, which we'll study later, but at least this was to just illustrate that the encryption mode that you're using, in fact, we're using very, very commonly, is based on counter mode. We can see how these things work, but implementations of all of these modes of operation are widely available, so you can play with them if you like and so forth. But there are also these online calculators. So here, for example, is a calculator where I can select a mode. For example, ECB is going to encrypt with AES if I give it a key and an initialization vector. So let's try. I need a key that's 16 digits, so as to be 128 bits, and a similar length for the initialization vector. So maybe that'll do it. That's hopefully 16 digits. Then I can enter a text and let's see what happens. Oh, something popped out, so we have a ciphertext here. Okay, let's see what happens if we try to decrypt that. So enter that as text to decrypt, and take the secret key, and decrypt. That did not work. What fun. Okay, I think the reason is I'm using ECB. Why do I have an initialization vector? So let's try that. Oh, did anything even change there? No. Decode to plain text. Okay, so it was working, sorry, just that this was base 64. So that's the decoding. It allowed us to enter an IV, but with ECB, it's not going to use it. Now, if you try another mode, you do need an IV. So if you try CBC, I'll need a 16-digit IB, and let's change the text so we would recognize it. We get something over there. Now, despite the fact that there is an IV, it should decrypt without access to that. So, given final block is not properly loaded, bad key is used during decryption. Something wrong with the key. Oh, of course, I'm supposed to CBC decrypt. Okay. That's the base 4 things. Decode to plain text. Seems to still have trouble decoding this. What happened with that? Okay. This is a nice illustration of the gap between software and theory, I suppose. But hopefully you get some sense of how things might work, and you can write better code yourself. Okay. So just quickly recap. We introduced CBC and counter mode, which are very popular schemes, as ways to add randomization so that we can achieve higher security, and in particular counter the attacks we saw on electronic codebook mode. So that means it would be worthwhile to check what happens with that same attack. So there we were encrypting either a yes or no message, and we were violating security by the fact that the ciphertexts communicated whether the messages were equal or not. Ciphertext equality and message equality occurred simultaneously. If you're now doing CBC encryption, when I encrypt M1, a random IV will be chosen, and encryption will happen like this, and this 2-block ciphertext is transmitted. When I now encrypt M2, a fresh random IV is chosen, and this 2-block ciphertext is transmitted. Suppose the adversary, as before, knows that the first message is a yes. Can it determine whether the second is yes or no? And the answer is that it seems pretty hard. How is it going to do that? These two ciphertexts, C1 and C2, are most likely going to be unequal no matter what. Whether M2 is yes or M2 is no, almost certainly they will be distinct. And so that at least is not giving anything away, and it is not clear how the adversary is going to get information. And so you see what's happened is we've gained the ability to add privacy even when there's very little entropy in the data, and that was something we lacked before this. However, we haven't yet established in any way that CBC is actually better than electronic codebook mode. Well, okay, we've established it's better, but we haven't established that it's secure, or that it can be used for arbitrary applications, or that it doesn't have some other weakness that we haven't spotted. After all, we saw that creative adversarial thinking led us to identify a problem with ECB. Why wouldn't something like that be true for CBC as well? So now we're going to tackle that question. How do we analyze CBC? And we realize that the first thing we need is a definition. We need to formalize what exactly we're trying to achieve with regard to privacy so that we can make meaningful claims and prove theorems about security. And so again, we go back to what's this sort of really core enterprise in modern cryptography, which is to think carefully about and then formulate precise definitions. And here we have as a task something extremely basic and quite intriguing, which is to ask how we formalize what it means for encryption to keep the message private. It's actually puzzling, maybe, that centuries or millennia of encryption design waited until Shannon and then further until the Goldwasser-Micali computational definitions to even ask a question like, what does it mean for encryption to preserve privacy of the message? And when you ask it, you see that it's not quite that simple. Our naive model is that the adversary has these Q ciphertexts obtained by encrypting a bunch of messages under a single but hidden key. And we can ask, what are the things that if the adversary succeeds at, we would get worried? Certainly one of them is that it retrieves the key. Key recovery is always a goal for the adversary that we want to deny it the ability to achieve. But what if it, for example, retrieves the first message but doesn't learn the key? Clearly that's still a problem, so we need to look beyond key recovery. But we've already seen that if it can just determine whether two encrypted messages are the same, we have a problem in the voting application. So ideally, a good encryption scheme will hide something like that. It should also hide things like partial information about the data. What is the first bit of the message? Even functions of the data. What is the sum of the first bits of two different messages? And so effectively, somehow we're looking for a way to hide everything. Just one caveat, we're not going to hide the length of the message. The message is a sequence of bits, and the schemes we're considering tend to reveal that length through the length of the ciphertext. Now, this is not something that we do because we think it's okay to reveal length. That can be quite a problem, and there are attacks based on that on various TLS applications. But it's not simple to, in a pragmatic way, actually accomplish length hiding. And so for the large part, the theory here punts on that. We saw on the last slide that you could consider a whole host of attributes that you'd like a secure encryption scheme to have. But that kind of list, just as we saw for PRFs, is not going to make a definition. So what we're looking for is a single master property, whereby you can easily specify it through games, evaluate whether a scheme meets it, and then get some assurance that it does what we want, in the sense that you will achieve the different other properties of interest once you have achieved this one in an automatic way. This property implies all the other properties. Okay, and so this leads us to our definition, which is called indistinguishably under chosen plain text attack. And we will describe it formally through games, but first let's give the intuition, which is actually covers it fairly well, in the extent that if you grasp this, you kind of can see what the games are doing very simply. In some ways, it says that the type of usage we looked at in the voting application is a worst case. It needs to be just extended a little bit. So we're going to consider a scenario where, to start out with, there are two possible messages, M0 sup1 and M1 sup1, just two messages. Think of Q here as being one. The adversary is going to encrypt one of them but you don't a priori know which one. You do know these two messages, and one of them will be encrypted. Again, it could be yes or no, the two votes. You're given the ciphertext, and your job is to figure out which of the two messages was encrypted. And if you can't figure it out, you violated IND-CPA security, and security thus requires that you somehow not be able to figure it out. Okay, now the extensions. The first extension, the encryption will not be of just one message, but of a lot of them, a number, because in practice we do encrypt lots of messages under a single key. So there is not just two messages now, but two streams. And both streams are public. The adversary knows exactly what all these twice Q messages are. One by one, the adversary encrypts either all these or all these. And our job, given the ciphertext, is to determine which of these two things happen. And you will get Q ciphertext here. Okay, the next step in the strengthening is that not only does the adversary know these messages, it even picks them. So the scheme might allow encryption of many possible messages. Maybe it becomes a vulnerability on certain messages. Certain messages are weak and encryption fails on them. If so, the adversary could pick those messages. So we let it choose which messages to pick, and that's the chosen plain text attack aspect. Okay, so now we simply turn that into games. And here they are. Now we're fixing a symmetric encryption scheme. This is the object whose security we're trying to measure. It could be any of the modes of operation we studied or something else, but it's public and fixed and known. There will be two games, just like in the PRF definition, called left and right. So let's look at what they do. Each has an initialized procedure that runs this key generation algorithm to get a key for the encryption scheme. Once the key is obtained, it's frozen inside the game. It's hidden, it's not provided to the adversary, but it's static for the rest of the game. What the adversary gets is a procedure called LR, which stands for left or right. This procedure takes as input not one message, but two messages. And in the left game, when the query is made, the adversary takes the left message, M0, and then it encrypts it. How does it encrypt it? Using this prescribed algorithm, this key, and running them. Since encryption is randomized, potentially it will make internal random choices. And it will return a ciphertext C, and that ciphertext is given back to the adversary. The adversary can call this oracle many times, as often as it wants, each time with a pair of messages, which are required to have the same length to reflect that we don't hide length. Okay, what is the other game? It's actually almost the same except for one bit. The only change is that when you call this oracle, what it encrypts is the other message, the right one. But it's the same named oracle, same type of interface. So now we see what's going on. The adversary will say, please encrypt either M0 or M1. Depending on the game, one or the other is done. And then it's going to try to determine which of those two things happened. Now, when you have any specific adversary, you can run it with either game. Since the oracles have the same names and interfaces, that makes sense. We think of the adversary as trying to output a 1 when it's in the right game and a 0 when it's in the left game to indicate the index of the message being encrypted. So let's look at the probability it outputs a 1. We can compute that in the left world and the right world separately, and they're denoted like this. This is the game, superscript the adversary to indicate it's running with that adversary. Again, we're not interested in the actual values of these, but in how close they are to each other. So we define the advantage as the difference between these two probabilities. It's associated to the fixed scheme whose security we are measuring, to the adversary mounting the attack, and the superscript is the name of the metric, which is indistinguishably under chosen plain text attack. So if this number is big, the adversary is doing well, and otherwise it's doing poorly. Okay, so again, this is kind of a central element and will arise often, and so it takes a little bit of time to get used to if you've never seen something like this before, but otherwise you can go back over it and hopefully figure things out. Now, one restriction it's important to remember and make about this definition is that it is required in a left or right query that the two messages have the same length. Additionally, also, they must be in the message space of the encryption scheme. Remember, we discussed message spaces in talking about the decryption correctness. And this reflects the fact that we are not aiming to hide the length of messages. If you write an adversary that violates this condition, you will find it very easy to break the schemes, but we would consider that invalid because that's just not part of what the game allows. Okay, now how do we interpret these advantages? There's some subjectivity there, but largely an advantage close to 1 means your adversary is doing well. It's violating the IND-CPA security of your scheme, and that means the scheme fails to be IND-CPA secure, at least as long as that adversary is practical. An advantage close to 0 means your adversary is doing poorly. This may optimistically be an indication that the scheme is good in the sense of IND-CPA, because at least it's resisting this one attack. But you would have to test other attacks as well to determine whether the scheme is really good. As before, by convention, we'll see negative advantages as adversaries doing badly, because effectively when we do things right, they should never arise. Of course, if you invest enough resources in the form of running time and number of queries, you can break any mode of operation, for example, by running exhaustive key search. But that might be quite impractical for modern ciphers. So we measure security by asking how well practical adversaries do at violating IND-CPA. So we quantify the running time and the number queue of Oracle queries, and based on those, we see what advantage one can get. So security in the sense of IND-CPA for our scheme would mean that this advantage is small for all adversaries as long as their resource usage is somehow practical. Conversely, insecurity would mean that the scheme fails to be IND-CPA if we can demonstrate an explicit attack or adversary which is practical. It doesn't use much in the way of resources, yet achieves an CPA advantage that's quite high, close to 1, but even 25% is considered high. Okay, now again, these are not precise or formal definitions, and that's what these quotes around terms indicate, and that's intentional because security is a determination of a user or an application. It depends on what the entities desire and what their views are of what adversaries are capable and so forth. And when we make estimates, we'll usually quantify things to make it possible to make good estimates. Now, these abstract definitions may need some mapping back to applications. The number of Oracle queries in usage is the number of messages encrypted. So Q is the number of messages that Alice encrypts, whereas T is the running time of the adversary in all of this. Okay, so before we go on to some example of that, we could again maybe look around at what the world is saying about these things. So here's a Wikipedia article on ciphertext indistinguishability, which is indistinguishable under chosen plain text attack or IND-CPA. And so it talks about that. It's a source of a definition. And so this is an indication of how these things are fairly well understood and accepted at this point. And it has games the same way we do. This game is actually modeled on one we'll see later in our chapter, not the ones we've seen so far. And with that, let's look at our example. So we now are going to assess the security of electronic codebook mode with our new definition. Now, why would we want to do that? We basically already determined that we think it's insecure, and it is. So, but we want to say, what does IND-CPA as a formal definition think about this? Does it view ECB as insecure or as secure? This is a test of the definition. If the definition declared ECB to be secure, we would have to throw away the definition. So we expect or hope that that doesn't happen, and the definition allows us to formally show that ECB is insecure. So let's do that. It'll exercise writing an attack as well. We fix our block cipher, which is well known, and let n be the block length. And we recall that the symmetric encryption scheme, that is ECB mode, will encrypt a message by simply applying the block cipher with the key independently to each block. So succinctly, it's this one-line formula. To attack it in the sense of IND-CPA, we're asking, can you design an adversary whose advantage in the IND-CPA sense is high, close to 1, even though it uses very few resources and is quite practical? That would be a demonstration of insecurity. Okay, so let's go ahead and do that. We already know intuitively what's wrong with this scheme. It simply is determinism. So we know that when two messages are the same, so are their encryptions. That's just a feature of this formula. So our job in building an attack comes down to seeing how to exploit that to actually give an adversary with high advantage. And so here's how we might do it. What our adversary does is say, okay, I need to call the left or right oracle. I don't know what the key is, but I know ECB is being used. I want to call the oracle in such a way that from the ciphertext that I get back, I can determine whether the left or the right message was encrypted. So I'm going to make two calls to left or right. Each of them has two messages, left or right. And the property they have is that in the left world, the two messages are different, 0 to the n here, 1 to the n here. But in the right world, they're the same. So if from ciphertext I can detect whether or not the encrypted messages are the same, I will be able to violate security. And ECB allows that because we know that equality of ciphertext and equality of plain text are the same. So this is what our adversary checks. It makes a call of LR with these two inputs, 0, 0, two messages, each one block long, and then again two messages, each one block long, first one changed to 1. Test whether the resulting ciphertext are the same. If so, declare you're in world right, this one, otherwise world 0. So we have our adversary. Let's go through the analysis, which establishes what its advantage is. Encryption is ECB. We haven't changed that. This is the formula. There's just one block, so really we're stopping over here. This is our adversary, and we start with game right. And I want to know the probability that the adversary running in that outputs a 1. So in this adversary, we see that it outputs a 1 when C1 equals C2. So we want to know, when does C1 equal C2? So what are C1 and C2? They are the outputs of LR, but in the right game, the messages encrypted are 0 and 0 because you choose the right message over here. So both times we get an encryption of 0. But now we exploit the fact that this is the encryption scheme, and it's simply a block cipher with a fixed key, hence deterministic. So EK of 0 is returned both times, and we will indeed have C1 equals C2. That happens regardless of the choice of key, so this probability is just 1. In the left world, we have the same adversary and the same scheme, and this adversary returns 1 under the same condition. What is it that's changed? The ciphertexts are computed differently. According to this, the left one of the two messages is encrypted both times, and both times under the same key. So here it's the 0, and here it's the 1. Okay, so now will these ciphertexts be equal or not? To determine that, we use the fact that we know how encryption is working. It's the block cipher applied to the message. So C1 is the block cipher under K applied to 0, C2 under 1 to 1. But we know that ECB K is a permutation because this is a block cipher. So in fact, these will never be equal. And hence, the adversary will never have this test triggered to true, and so it will never return 1. It will always return 0. Probability of returning 1 is thus a 0. Subtracting those two gives us an advantage of 1. Additionally, the adversary was extremely efficient, making only 2 queries, so we can conclude that electronic codebook mode is not IND-CPA secure, thereby backing up our informal intuition about its insecurity with the formal claim that helps us validate the definition and also invalidate ECB. You can redo this by seeing that this attack is easily modified to show that any encryption, symmetric encryption scheme with a deterministic encryption algorithm can be shown to be insecure in the same way. And here are other such attacks.